Settle in and let your breathing slow, like a countdown you do not have to watch. The room is quiet, and somewhere far above it, a spacecraft is being treated like a very careful appliance. Checklists turn softly, voices stay low, and nothing dramatic happens on purpose. Tonight, you are going with them, not as a hero, but as a patient observer of routine. You will drift through a small, humming cabin, watch Earth fade into a bright marble, and finally step into the moon's dry, powdery stillness. And when it is time to collect the rocks, you will find that the most fascinating part is how ordinary it feels, one labeled bag at a time, with the Sleepless Scientist keeping you company in the dark. You think a launch is an explosion of emotion, a sudden leap from Earth to legend. But what you actually get is paperwork, spoken out loud. You get hands moving in practiced loops. Switch, confirm, read back, confirm again. The spacecraft is not a stallion. It is a complicated office printer that happens to ride fire. You are strapped in, and you can feel the suit pressing into your shoulders. Not painful, just insistent. The air smells faintly metallic, like warm electronics. You hear fans pushing oxygen through hoses, and you realize this whole trip is going to be measured in the sound of machinery that refuses to stop. A voice comes through the headset. Calm enough to be boring? That is the point. Boring means controlled. Boring means nobody is improvising. The Apollo era did not worship spontaneity. It worshipped procedures, because procedures are what you do when the universe does not care. Under you, the rocket is being fed. Propellants are flowing into tanks through thick lines, and you never see any of it. You just feel the distant shiver of valves opening and closing. Liquid oxygen is so cold, it would bite through skin in seconds. Kerosene, in its refined rocket form, sits ready to burn like a disciplined rage. But up here, inside your small capsule, it is all translated into quiet indicators and simple words. The checklist continues because the checklist is the real engine. Each item is a tiny superstition made of engineering. Verify pressure, verify voltage, verify the thing that keeps you alive is still alive. And then the moment comes, and it still feels like work. At ignition, you do not float. You do not drift into the heavens. You are pressed downward, firmly, like a heavy hand on your chest. The vibration is not a clean shake. It is a complicated trembling that crawls through your bones. The sound is not a cinematic roar, because the capsule is built to keep sound out. What you get instead is a muffled violence, like thunder behind a wall. You rise anyway. You are climbing through air that gets thinner and thinner, and the first strange thing is how fast the world becomes, not silent, but different. On the ground, sound is everywhere. Insects, wind, engines, distant human noise. Up here, the outside stops carrying sound. The rocket still shakes, but the sky stops answering. The atmosphere is falling away beneath you, and you cannot hear it leave. The spacecraft is small, but it is full of tiny decisions, gauges, needles, caution lights that are meant to stay dark. Everything is redundant because space is not impressed by your confidence. There are backups for the backups, not because you are paranoid, but because you are realistic. You feel stages separate as a gentle lurch, a clean mechanical release. The rocket sheds parts the way a snake sheds skin, leaving them behind without nostalgia. Those empty shells tumble down toward Earth, toward air, toward heat, toward a violent end. You do not watch them. You just feel the next engine take over, and you keep climbing. The horizon curves in a way your brain refuses to accept at first. It does not feel spiritual. It feels like seeing a familiar room rearranged while you were gone. Earth becomes a place instead of the place, blue, white, and thin, with a fragile line of atmosphere, like a breath held around a planet. And eventually, the push eases. The pressing weight on your chest softens. The straps stop digging quite so hard. Your stomach shifts, unsure what rule it should follow now. Congratulations, you are in orbit, which is a fancy way of saying you are falling around Earth forever, as long as you keep missing it. Now the cabin becomes what it really is, a small, humming room full of controlled air and soft noises. There is no triumphant music. There is only the ventilation system doing its steady job like a tired employee. Fans, pumps, the occasional click of a relay. You begin to understand that the soundtrack of space travel is not silence. It is life support. The crew does not celebrate for long. There is always another checklist, another sequence. The Apollo missions were stitched together from thousands of steps that had to be done correctly, in order, every time. The drama people remember is the external view. The internal view is closer to doing taxes during an earthquake. You look through a window and Earth is already pulling away. Not because you are leaving it quickly, but because distances in space are rude. A small change in position becomes a huge change in perspective. Continents slide under cloud, and the ocean looks like glass with weather trapped inside it. Then comes the long departure. The translunar injection burn, the push that sends you out of orbit and toward the moon. It is not a sudden slingshot in your body. It is a sustained, controlled acceleration that feels like being leaned into. Slowly, the engine burns for minutes, and those minutes matter more than speeches. When the burn ends, there is a new kind of quiet. Not empty, just settled. You are no longer circling home. You are committed. Outside, Earth keeps shrinking. It becomes a bright marble, and then something smaller. It is still loud in your mind, of course, but visually, it is just a glowing coin in blackness. That is the first emotional trick space plays on you. It makes the most important thing you have ever known look pocket-sized. And once Earth becomes a bright marble in the window, the trip turns into something surprisingly ordinary and very, very quiet. Ordinary means you still have to eat. In microgravity, food is not a meal. It is a management task. The Apollo-era menu was practical. Cubes, paste, dehydrated packets you rehydrate with measured squirts of water. The flavors, fine, not terrible, not exciting. The kind of food you eat because your body is a machine too, and the machine needs fuel. You squeeze a package and watch a blob form at the opening. It clings there, surface tension holding it together like a stubborn thought. On Earth, gravity would pull it down. Here, it just sits, rounded and glossy, waiting for you to bite it off and guide it into your mouth. Nothing falls, everything floats, but not freely. It sticks to surfaces, to fingers, to itself. Water is stranger. You do not pour it. You do not sip it from an open cup. You drink from bags and valves, carefully, because a spill is not a puddle. A spill is a swarm. A bead of water escapes, and it does not drop. It becomes a little drifting planet of its own, wobbling through the cabin. It reflects panels and faces in miniature. It looks cute until you remember what it can do. Water can invade switches. It can creep into connectors. It can turn electronics into dead weight. So you chase it, slowly, because every movement sends you in the opposite direction. You pin it with a cloth, and the cloth drinks it up. It is a tiny chore, made difficult by the lack of down. In Apollo, clutter was the enemy. Every object had to be tethered, stowed, or clipped. A pencil drifting into the wrong place could jam a switch. A small tool could become a projectile if the spacecraft jolted. Even a crumb was a problem. Crumbs do not politely fall to the floor. They hover, they migrate, they wait for your lungs. So cleaning becomes part of the day. Wiping down surfaces, collecting stray particles, managing the cabin as if it is a small submarine, except the ocean outside is vacuum. And you sleep, if you can call it that. You strap yourself into a sleeping bag, because otherwise you would drift. You close your eyes and your body tries to interpret the new signals. Your inner ear complains. Your stomach has opinions. Some astronauts felt space motion sickness in the first days because your brain expects gravity like it expects language. Without it, it gets confused. Then it gets angry. There is no true night and day unless you make it. In orbit, sunrise and sunset come too quickly to mean anything. On the way to the moon, the light is steadier, but time still feels unmoored. So routines become the clock, meals, maintenance, navigation checks. The rhythm of tasks replaces the rhythm of the sky. And all the while, the cabin has its constant background noises. The ventilation, always there, always pushing. The pumps moving fluids through systems you never see. The soft static of radio. The occasional beep of an instrument reminding you it is awake. It is easy, after a while, to find that sound comforting, because sound means air is moving. Sound means you are not in a dead capsule, silently freezing and asphyxiating. That is the cozy horror of it. Your lullaby is a machine. Your atmosphere is an appliance. And you learn to love it because it loves you back in the only way it knows how, by continuing to function. Sometimes you look out the window and the stars are sharper than you expect. On Earth, the air blurs them. It scatters light and dims the faint ones. Up here, there is no air to soften anything. The darkness is hard and clean, like a polished surface. Stars do not twinkle. They just stare. You might expect the spacecraft to feel like a cathedral of technology. It does not. It feels like a cramped workspace. Switches, labels, wires hidden behind panels. Your knees come up close. Your elbows find edges. The Apollo era was not designed for comfort. It was designed for survival and function. And those two things are not always friends. And still, the days pass and the moon grows. At first, it is a disk you have known your whole life, now simply closer. Then it becomes textured. You begin to see the difference between the dark Maria, those ancient basalt plains, and the brighter highlands. The moon stops being a symbol and starts being a world with geography. That rhythm carries you onward until the moon stops being a destination and starts looking like a place you could almost touch. As you approach, the first surprise is the color. The moon in your memory is bright white, like a lamp in the night sky. Up close, it is not white, it is muted, grays and dusty browns, with tones that shift depending on the angle of the sun. It looks like old stone, sun-bleached and tired. And the shadows. The shadows are not gentle. They are not soft gradients like you see on Earth. There is no atmosphere here to scatter light into the shaded places. On Earth, even in shadow, the sky leaks in. Blue light bounces around, filling darkness with a faint glow. On the moon, shadow is a hard absence. A crater rim cuts sunlight like a knife, and the inside drops into black. You stare at those shadows and feel something old in your body, a part of you that learned long ago that darkness can hide teeth. But this darkness is not hiding anything. It is just emptiness. It is the simple result of air not existing. The surface is scarred, and those scars are time made visible. Craters overlap craters, layered like memories that never fade. On Earth, weather erases. Wind, water, ice, plate tectonics, the planet constantly rewrites itself. The moon does not rewrite, it keeps receipts. Each crater is the aftermath of an impact, a moment when something from space met the surface at speeds that turn rock into vapor. You imagine the violence, and then you look at the stillness now. It is like walking into a room long after an argument ended, when only the broken furniture remains. Some craters are young, sharp-edged, with rays of bright ejecta splashed outward like powdered paint. Others are old, softened by countless micrometeorite strikes, their rims worn down grain by grain. The moon has been sandblasted by space for billions of years, and yet it still looks crisp, because there is no rain to smooth it. As you draw closer, the moon fills the window, and you feel the spacecraft rotate gently for orientation. The approach is not a dive. It is careful, calculated, like docking at a quiet harbor where the water is black and the pier is made of ancient stone. To enter lunar orbit, you burn the engine at the right time in the right direction to let the moon's gravity capture you. Gravity is not a hand reaching out. It is a curve in space, and you are sliding into it like a marble into a bowl. When the burn ends, you are circling the moon. You pass over the bright highlands, pocked and rough. You cross over the dark plains that were once lava flows, long cooled. You see mountains that are not mountains in the Earth sense, because they were not pushed up by plates grinding together. They are uplift from impacts, rims thrown high by force. Below you, everything is frozen in place. No trees, no rivers, no smoke, no weather, just rock and dust under harsh light. And that harsh light makes the landscape feel both flat and jagged at the same time. Without atmospheric haze, distances are hard to judge. A boulder could be the size of a fist or the size of a car. Your eyes are used to cues that are missing here. You keep circling, and each orbit is a slow rehearsal. Systems checks, navigation verification, alignments and timings. The moon is a place you do not simply visit. You negotiate with it politely, through math, and when you finally settle into lunar orbit, you realize the next step is not speed, it is patience. The lunar module is waiting, folded and awkward, like a mechanical insect. It was built for one job, and it shows. It does not need to be sleek in air because there is no air. It needs to function in vacuum, in dust, in brutal temperature swings, and in the quiet indifference of low gravity. You move through procedures to separate it from the command module. The act is gentle, but the meaning is heavy. In the command module, a portion of your ride home remains. In the lunar module, you have something else: a descending room, a temporary shelter, and an engine that has to work twice, once to land and once to leave. You climb inside, and the space feels even tighter, more utilitarian. Panels close enough to touch with a gloved hand, windows angled for visibility, everything designed around the reality that you will be wearing a suit and that your fingers will be clumsy inside pressurized gloves. Undocking is controlled, a slow separation, like letting go of a dock line. The command module drifts away, still circling, still waiting. You are now in the smaller craft, the one that will go down. The descent begins with a burn that changes your orbit, lowering the point where you will pass close to the surface. You watch numbers and listen to callouts. Altitude, velocity, fuel. The language is calm. It has to be. As you drop lower, the surface begins to move beneath you. Features slide past, craters, ridges, scattered boulders. The moon is not actively trying to kill you. It does not need to try. All it has to do is exist. The descent engine ignites, and you feel a steady push. Not violent, just firm. A controlled resistance against gravity. You are not falling anymore. You are negotiating the rate of your fall. The lunar landing is often remembered as a single heroic moment. The reality is a long sequence of tiny corrections, a slow conversation between sensors and human judgment. The engine burns and fuel ticks down. The clock is quiet, but it is there. You glance out, and the surface looks closer than it should. The lack of atmosphere makes everything sharp, and it tricks you into thinking you are lower. Shadows are pitch dark. Sunlit areas are bright enough to feel like they would burn your eyes even through the window filters. Dust begins to stir beneath you as you get closer. The exhaust hits the surface and kicks up regolith, the fine, broken rock layer that covers the moon like old flour. It does not billow like smoke. It sprays and skitters because there is no air to carry it. It moves in ballistic arcs, obeying only gravity and momentum. You are hovering now in that strange phase where the moon is right there, and yet you are not on it. It is like trying to park over a surface that has no depth cues, no familiar scale, just harsh light and dark. Then, a small signal, a contact light. Something touches. The engine cuts, and the shift is subtle. You are down, not with a thud, not with a cinematic bounce, just a settling, as if the world finally accepted your weight, such as it is here, and arriving is only the beginning, because now you have to step outside into a place that does not care you are there. But that step is not immediate, not if you like living. First, there are post-landing checklists, safing systems, confirming stability, making sure nothing is leaking, nothing is overheating, nothing is quietly becoming a disaster. The cabin air is still the same manufactured comfort, and you are still behind metal walls. Outside is vacuum, a temperature swing waiting to happen, and sunlight that feels too honest. You begin suiting procedures. In the Apollo era, the suit was not a costume. It was a personal spacecraft wrapped around your body. Layers for pressure, layers for thermal control, layers for micro-meteoroid protection. A backpack life support system that provides oxygen, scrubs carbon dioxide, regulates temperature, and circulates water in tubes close to your skin. You do not simply put it on. You assemble it around yourself, and every step is slower than you want it to be. Gloves make fingers thick. Connections require attention. Valves must be in the right position. Seals must be clean, because a tiny leak is not a gentle problem. A tiny leak is an emergency that starts whispering and then does not stop. When the suits are pressurized, you feel them stiffen. Your movements become more deliberate. You become aware that the suit resists bending. It is like moving inside a firm balloon. You prepare the cabin for depressurization. You close valves. You check gauges. You accept, in a quiet way, that you are about to remove the air from your room on purpose. Then the pressure drops. You might expect a dramatic rush, but the system is controlled. The air leaves steadily, and the sound changes. Fans shift tone. Your ears feel it. The cabin becomes a different kind of place, a metal shell with nothing inside but you, sealed within your own bubble. When the hatch opens, there is no whoosh, no wind, just a door moving and blackness beyond, and the gray ground waiting. You climb down the ladder slowly. Each rung is deliberate. You are aware of your center of mass. In low gravity, you are lighter, but also easier to tip. The suit limits motion. Your backpack shifts your balance. You have to learn your body again. And when your boot touches the surface, it does not crunch like sand at the beach. It compresses. It yields in a fine way, like powder that has been dry for a very long time. The regolith is made of shattered rock, ground down by impacts. No water to round the grains, no wind to soften edges. The particles can be sharp, like tiny broken glass. You press, and a footprint forms with crisp edges. It stays. No breeze will blur it. No rain will fill it. Your step becomes a mark that might last longer than the buildings you live in. Moving is strange. You try to walk normally, and your body wants to bounce. The best way becomes a kind of hopping gait, a lope. Each push sends you farther than expected. Each landing is slower. You are in a world where your weight is reduced, but your mass is not. You are still you, still stubborn, still unwilling to change direction quickly. You pick up a tool and you feel the suit's resistance. You reach out and realize depth perception is odd through a helmet visor. You are always aware of the glass between you and everything else. Every task becomes a small ritual. The dust clings, it finds surfaces, and holds on. On Earth, dust is usually rounded and mixed with moisture and organic bits. Lunar dust is dry, fine, and electrostatically charged by sunlight and particle impacts. It behaves like it is personally offended by cleanliness. It coats boots, it gathers on knees, it sticks to gloves, it dulls shiny parts. Later, when you go back inside, it will come with you, and the cabin will smell faintly of it. An odd scent astronauts described as like burnt gunpowder. Not because it is burning, but because the dust is chemically reactive, fresh fractured minerals eager to meet oxygen after a long time alone. The landscape up close is made of rocks that look ordinary until you remember the timescales. A stone on Earth has been rained on, heated, cooled, broken, buried, uplifted, eroded, handled by biology. Here, a rock can sit in place for millions of years and still look sharp. It can be a fragment thrown out of a crater long ago, resting where it landed. Some rocks are angular, some are smoother, coated in dust. Some are fused, glassy, formed when impacts melted the surface and splashed it into droplets that cooled quickly. You are walking through a museum that does not label exhibits because the moon does not care about your education. But you do, so you start doing the work. You hold a camera and you take photographs before you touch things. Not because you want souvenirs, but because context is everything. A rock without context is just a rock. A rock with location, orientation, nearby features, and depth notes becomes data. You might think collecting moon rocks is the exciting part. The reality is quieter. It is fieldwork with gloves on, under a harsh lamp, with your life support ticking behind your shoulders. And as you learn how to exist on the surface, your attention naturally drifts to the main prize, the rocks under your boots. You kneel slowly because kneeling in a pressurized suit is an argument. The suit resists bending, and you have to work with it instead of against it. You steady yourself, and you bring out a scoop or tongs, tools designed for hands that cannot feel. A sample bag waits, pre-labeled, because nobody trusts memory in a hostile environment. Each bag has an identifier, and the identifier is tied to notes and photos and timelines. The rocks are not collected like treasure. They are collected like evidence. You select a piece of regolith first, the fine soil. It is not soil in the earth sense. No living things, no organic matter. But it is the surface layer that records micrometeorite impacts and solar wind particles. It is the moon's exposed skin. You scoop carefully, and the material pours in a slow arc. Because gravity is weaker, the dust grains do not clump. They slide and settle like dry powder. You seal the bag, and you can almost feel the future lab technicians nodding in approval. Somewhere on Earth, years behind you. Then you move to rocks. You choose variety on purpose. The mission planners wanted different kinds because different kinds tell different stories. Basalt from the Maria, those dark lava plains, speaks of volcanic activity. And Northosite from the highlands speaks of the moon's early crust, lighter minerals floating when the moon was molten. Breccias, rocks made of broken fragments fused together, speak of impacts and violence. Glassy beads speak of melt and splash. So you look for textures and colors, even though the colors are subtle. A slightly different shade of gray can matter. A surface with tiny sparkles, crystals catching light, can matter. A rock with a rounded glass coating can matter. You pick up one piece, and it feels lighter than you expect, not because it is less dense, but because your muscles are recalibrating. Another piece looks like plain stone, but the edges are sharp, and you imagine it was created when an impact shattered bedrock and flung it across the surface. You place samples into bags, into containers, into a chain of custody that begins here, under your boots. Every time you seal something, you are sealing time. You are trapping a tiny piece of the moon in a human system of labels and records. This is where the boredom becomes fascinating, because the act is repetitive. Kneel, scoop, seal, note, stand, shuffle, photograph, repeat. You are doing what geologists do on Earth, except your field site has no wind, no birds, and no mercy. You take core samples in some missions, driving a tube into the regolith to capture a vertical column. The layers matter. The top layer is more exposed to space weathering, bombarded by charged particles and micrometeorites. Deeper layers are older surfaces, protected, quieter. When you pull the core out, it is like extracting a timeline, compacted dust and fragments stacked in order. The tools are designed to be simple, because simple survives. Tongs to avoid touching with gloves that might contaminate, scoops with edges that can cut into compacted soil, rakes for small fragments. A documented sequence, because the point is not just to bring rocks home. The point is to bring home a story that can be read later. And contamination is always lurking, like an uninvited guest. The Apollo sample handling was careful because Earth is messy. Your suit carries traces of materials. The spacecraft carries traces of manufacturing. Even your breath, if it ever touched a sample, would change it. So procedures exist to reduce that. Bags are sealed, containers are closed, some samples are placed in vacuum-tight boxes to keep them as close to lunar conditions as possible. Not perfect, but better than careless. You may feel, in this moment, that you are doing something historic, but it still feels like work. The moon does not applaud. The only sound you hear is your breathing in the headset, the faint hiss of oxygen flow, and the occasional calm voice over the radio. You look out and the horizon is close, because the moon is small. The curve is noticeable. It makes you feel like you are standing on the shoulder of a giant stone ball. Above, the sky is black, even in daylight. The sun is a glaring presence, but it does not turn the sky blue. There is no air to scatter its light, just direct beams and hard shadows. And the Earth, if you see it, hangs there, bright and distant, a marble again, watching without blinking. You go back to work. You collect a rock that looks glassy, and you remember why. Impacts can melt rock instantly. Melt can pool, splash, spray, then cool into glass. Some lunar samples contain agglutinates, clumps formed when micrometeorites melt dust and fuse grains together with tiny droplets of glass. The surface is constantly being processed by impacts, a slow cosmic grinding. You collect another rock with pale crystals embedded in darker matrix. That contrast hints at different cooling histories. Bigger crystals can mean slower cooling, deeper underground. Fine grains can mean rapid cooling, lava exposed to vacuum. Each texture is a clue. You do not solve the mystery here. You just gather the pages. And sometimes, the moon offers tiny surprises. A rock that breaks easier than expected. A patch of soil that looks slightly different, more compacted. a boulder that casts a shadow so dark it feels like a hole in reality. You approach carefully, because the shadow might hide a slope, and slopes are how you fall. Low gravity makes falls slow but not harmless. You can still break equipment. You can still puncture a suit. You can still turn a routine moment into an urgent one. So you move carefully, always carefully, like someone walking through a room full of sleeping animals. The collection continues, bag after bag. Each one is sealed, labeled, and mentally placed into a map in your mind. Near the lander, by the crater rim, along the traverse path. Context, 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 because without it, the rock becomes mute. In the Apollo era, they brought back hundreds of kilograms of material across missions, but no single rock mattered as much as the whole set. Variety matters. Distribution matters. The boring repetition is what creates a data set. And eventually, you glance at the time and you feel the soft pressure of limits. Oxygen is finite. Cooling water is finite. Battery power is finite. You cannot stay forever, no matter how quiet it is. So you begin the slow process of gathering your gathered things. Everything has a place, even here. Especially here, you clip the sealed bags to a strap, one by one, feeling the little tugs as they settle. Each bag is soft and unremarkable until you remember what is inside. Not gems, not trophies, just gray fragments that have never tasted rain. You look down at your boots, and the dust has climbed them like it owns you now. It has packed into the treads, darkened the edges, dulled the clean lines of your hardware. Lunar regolith is not polite dirt. It is fresh, broken mineral, sharp and clingy, and it behaves like it wants a long-term relationship. You do a quick check of the area because your mind is trained to scan. Tools accounted for, bags secured, nothing left drifting, nothing left unsealed. On Earth, forgetting a wrench is a bad day. Here, forgetting a wrench could become a jammed hatch, or a torn glove, or a story people tell in a safety briefing later. You lift your arm and glance at the readouts on the suit. The numbers are not comforting. They are simply honest. Oxygen pressure, cooling water, battery power, all quietly counting down. Your life is a slow leak that you refilled earlier. Congratulations! You have discovered that exploring another world is mostly inventory management. You make your way back toward the lunar module, moving with that careful lope you have learned. Step, float, settle. Step, float, settle. Each landing sends a small puff of dust outward in a lazy arc. It does not hang in the air. It does not swirl. It simply falls back down, as if the moon is tired of your theatrics. As you approach the ladder, the lander looks stranger than it did in orbit. Up close, it is all angles and foil, like something a clever person built in a garage out of sheet metal and stubbornness. The gold-colored insulation is not decoration. It is a thin barrier against temperature extremes that do not negotiate. You pause for one last look around because your brain will want a memory that is not filtered through procedures. The horizon curves close, the sky stays black, and the sunlight is still that hard, unsoftened beam. No haze, no mercy. The scene looks like a photograph that forgot to include warmth. Then you climb. Each rung is a slow argument with the suit. Your knees do not bend the way you want. Your boots feel big. Your gloves feel like they are made of inflated rubber, because they are. You keep your movements smooth because anything abrupt makes you bounce, and bouncing makes you clumsy, and clumsy makes you dead. At the hatch, you stop and start the ritual of getting the moon back out of your life. You brush at the dust with a tool, not because you can clean it, but because you can reduce it. Apollo crews did what they could because everyone learned quickly that lunar dust was a small villain. It scratched visors, it clogged joints, it wore at seals, it got into the cabin and floated, and then it got into noses and throats later, where it behaved like the world's driest pepper. You secure the sample containers inside the cabin, and you treat them like fragile evidence, not because they will break easily, but because context can break easily. Labels can smear, bags can tear. A mixed sample is not just a mess, it is a question mark that never goes away. You close the hatch, and you prepare to bring air back into your little room. The repressurization is controlled, steady, and a little anticlimactic. The cabin pressure rises, and sound returns in layers. A faint hiss becomes a fuller rush. Metal creaks gently as it takes the load. The first breath you take without the suit's loop feels thick and intimate, like you are drinking air instead of breathing it. Then you take off the helmet. The smell arrives almost immediately. That odd toasted odor, like spent matches or burnt gunpowder, or a fireplace that was cleaned too late. It is the dust, now meeting oxygen and moisture, now reacting in small chemical ways that your nose interprets as fire. It is not dangerous in the dramatic way, but it is irritating. Eyes itch, throats feel dry. You wipe your face and leave a streak of gray on fabric, and you think briefly about how this powder has been sitting in vacuum for so long, and how quickly it has invaded your human space. You and your crewmate stow gear, wipe surfaces, tuck cords away. The cabin is too small for chaos. If something floats into the wrong place, it will do it slowly, patiently, like a problem that enjoys suspense. And when you finally sit, the fatigue arrives in a wave. Not because you ran a marathon, because you did everything through resistance. Every motion fought the suit. Every thought fought the checklist. Even excitement is exhausting when it has to stay quiet. You take one more look through the window, at the surface, at the footprints, at the scattered tools, at the places where you disturbed a world that does not heal. The marks will remain. The dust will settle and then remain. The moon is good at keeping records, but the schedule does not care about your feelings. Leaving is not romantic. It is mechanical. You begin preparing the ascent stage, the top half of the lunar module that will lift you back to orbit. The lower stage, the descent stage, will stay here like an empty shell, a platform, a monument made of aluminum and foil. It will sit in silence for a very long time, until micro-meteorites sand it, until sunlight bakes it, until it becomes just another artifact in a museum with no visitors. Inside the cabin, switches are flipped, systems checked. You confirm guidance alignment. You confirm the engine is ready. You confirm you have not accidentally packed the one critical connector under a pile of bags like an absent-minded traveler. It is all so ordinary and so final. Then the engine fires. The ascent from the moon is not a roar you hear. It is a force you feel and a scene you watch. The window shows the surface dropping away, dust spraying outward, and then the lander's base shrinking below you. You rise into blackness like an elevator leaving a basement that never had lights. There is no atmosphere to shake you, no air to buffet. The flight feels smooth compared to the violent climb from Earth. But your mind knows the stakes because there is no runway here, no rescue helicopter, no second chance. The ascent engine is a single point of trust, and you ride it like you ride a promise. Below, the landing site becomes a small patch of gray, then just another cratered texture. The footprints become invisible. The place where you stood becomes anonymous again. The moon forgives you by ignoring you. You arc into orbit, matching the planned path. Everything is timing. Everything is geometry. Rendezvous in space is not chasing. It is arriving at the same place at the same time, like an appointment where being late means drifting forever. Somewhere above, the command module keeps circling, lonely and dutiful. One astronaut has been up there the whole time, listening to the radio, watching the surface slide by, keeping the ship ready. It is an odd kind of trust, leaving the person in orbit while you go down to another world and promising to meet again in a sky with no roads. The rendezvous procedures begin. You watch the indicators. You listen to calm voices. The lunar module adjusts its orbit with small burns, nudging itself into the right plane, the right height, the right timing. It is like lining up two invisible clock hands. When the command module comes into view, it looks impossibly clean and familiar. A shape you recognize, a reminder of home, even though home is far away and shrinking. Docking is careful, slow, a steady approach, closing speed measured in feet per second, spoken softly, as if loud voices might disturb the physics. Contact, capture, then the firm mechanical clunk of latches doing their job. For a moment, everything is still again. You equalize pressure between the two vehicles. Hatches open. Air mingles. The crew reunites. There is no grand embrace. Not in the way people imagine. The suits are in the way. The cabin is cramped, and there is work to do. But the relief is there, sitting under the surface of every word. Then the samples come through. You pass the containers hand to hand, careful not to bang them against frames. The rocks move from the lunar module into the command module, because the command module is the only part going all the way home. The lunar module has done its job. It can be discarded now. There is a quiet ruthlessness to Apollo hardware. Things are loved only as long as they function. When their usefulness ends, they are cut loose without ceremony. It is not cruelty. It is survival with a budget. Before jettison, you take one last look at the lunar module's interior. Scuffed surfaces, dust in corners, tether points, checklists taped where eyes naturally fall. It looks like any cramped workplace after a long shift. Then you close the hatch. You separate. The lunar module drifts away, a little insect shell tumbling gently. Some missions crashed it into the moon on purpose later to generate seismic signals, a deliberate impact. One last usefulness extracted from the machine. Speaking of impacts, the moon has been practicing them for billions of years. Humans just learned to schedule them. Now you are back in the command module, the small cone that will carry you through re-entry. It feels almost roomy compared to the lunar module, which is a strange thing to think in a space the size of a car interior. Perspective is a flexible organ. The return trip begins as another stretch of routine. Navigation checks, course corrections, equipment stowage, meals that taste like practical decisions. Sleep, that happens when it can. The moon falls behind you, becoming a disk again, then a bright coin, then just one more object in black. Outside the window, Earth slowly grows. The marble becomes a larger marble, then a world again. Clouds begin to show texture. The blue deepens. The thin atmosphere becomes visible as a faint limb, a delicate edge that holds everything you have ever breathed. And inside, the spacecraft hum continues. Fans, pumps, radio. The steady mechanical lullaby that means you are not dead yet. You spend time securing the samples. The containers are strapped down, cushioned, placed where they will not slam during maneuvers. You think about how unromantic this is. Not an altar, not a velvet box, straps and brackets and foam. But that is how you protect something priceless. You treat it like cargo. The Apollo samples had special sealed boxes and procedures designed to keep them as clean as possible. Some were sealed on the moon in vacuum-tight containers. Some were stored in ways that limited exposure to the command module's cabin environment. Not perfect, but intentional. Because Earth contamination is easy. It is everywhere. Skin oils, fibers, humidity, microbes. The world is thick with life, and life is sticky. The moon is not. The moon rocks are, in a way, sterile. Not sterile like a hospital. Sterile like a desert that never had water. They carry no biology, but they carry chemical stories that can be overridden by moisture and oxygen if you are careless. Some minerals change when exposed. Some surfaces hold implanted particles from the solar wind, atoms embedded like tiny souvenirs of sunlight. Those can be disturbed by heat, by handling, by time. So you handle them like evidence from a crime scene, where the suspect is the early solar system. There is something slightly absurd about it. Humans who shed skin constantly trying to keep another world clean. Congratulations, you are the contamination risk. On the way back, you do small tasks that make the difference between a smooth return and a complicated one. Checking the heat shield integrity indicators, verifying battery status, making sure the guidance computer is still the guidance computer and not a box that decided to sulk. The guidance computers in Apollo were miracles of their time and also comically underpowered by modern standards. They were designed for a narrow purpose, and they did it reliably, which is more than you can say for many modern devices that have opinions about software updates. The computer did not need to play music. It needed to keep you from missing Earth. And the navigation itself is a calm practice. Star sightings through a sextant, aligning the platform, confirming attitude. It is old school, almost nautical, except the ocean is vacuum and the lighthouse is a planet. Speaking of oceans, Earth's looks almost unreal from here, not because it is beautiful, though it is, but because it looks wet. Space makes water look like a miracle, and also like a vulnerability. Eventually, the time comes to prepare for re-entry. This is where the trip stops feeling like drifting and starts feeling like falling again. You stow loose items, you strap in, you confirm the capsule is configured correctly. The service module, the part with the big engine, and most of the power systems is no longer needed. It is jettisoned, left to burn up in the atmosphere later. A bright streak no one connects to the quiet work it did. Now, it is just you in the command module, a cone with a heat shield, aiming at a thin layer of air like it is a mattress. It is not a mattress. It is a grinder. The first kiss of atmosphere is gentle in a way you almost do not trust, but it builds fast. The capsule begins to heat. Air molecules, once sparse and ignored, now become a solid wall at orbital speed. They compress, they heat, they turn into plasma around the capsule, a sheath of glowing gas that carries away energy by being sacrificed. Outside, it is fire. Inside, it is vibration and growing deceleration. The straps bite again. Your body becomes heavy, heavier than you remember, as gravity returns not as a welcome home, but as a blunt instrument. The capsule shakes. It chatters. It feels like a washing machine with anger issues. The heat shield does its job by burning away in layers, ablating, carrying heat off as it erodes. It is engineered destruction in the service of survival. There is a period of radio blackout because the plasma around the capsule blocks signals. For a few minutes, you are alone in a very loud way. You cannot talk to anyone. You cannot hear anyone. You can only wait and trust that the math was right. Then the plasma thins. Radio returns. Voices come back, calm and familiar. Parachutes deploy later, and the violence becomes a different kind. First the drogue chute, stabilizing. Then the main chutes, snapping open with a tug that makes your spine notice. The capsule slows, sways, and the ocean rises beneath you. Splashdown is a final bump. Not gentle, but survivable. Water slaps the hull. The capsule rocks. After vacuum and silence and dust, the wet noise is almost shocking. The hatch opens, and humid air floods in, heavy with salt and life. The smell is thick and alive, full of things that grow and decay and breathe. You taste it immediately. Earth does not do subtle. You are back, but the rocks are not done traveling, because now they go from spacecraft to quarantine to lab. And their real job begins. The first steps on Earth are strangely controlled. Not because anyone doubts you are human, but because the Apollo era had a cautious imagination about what might come back. They built the Lunar Receiving Laboratory, a place designed to keep the samples isolated at first. Astronauts went into quarantine. Rocks went into glove boxes. Everything was handled with procedures that assumed, for a moment, that the moon might have something to share. It probably did not, but probably is a word engineers hate, so the samples are treated like they are precious and suspicious at the same time, which is, honestly, fair. You can imagine the scene, a clean facility, bright lights, people in protective clothing moving carefully. The rocks, gray and quiet, sitting behind glass, tools reaching in through thick gloves built into the glove box walls. A controlled nitrogen atmosphere sometimes used to reduce reactions with oxygen and water vapor. Every motion recorded, every container opened with attention. The rocks are weighed first. It sounds boring, and it is. But mass matters. Mass is the simplest property, and it is a baseline for everything else. You want to know how much material you truly have, and you want to track it as pieces are subdivided. Then comes photography. Again, high-resolution images under controlled light. You want to capture the surface before you cut it, before you polish it, before you expose fresh interiors. The outside of a lunar rock is not just outside. It can be coated in a glassy rind from impact melting. It can be peppered with tiny pits from micrometeorites. It can be darkened by space weathering, implanted ions from the solar wind altering its topmost layers. Space weathering is a gentle name for a steady assault. The surface is bombarded by protons and heavier ions from the sun. Micrometeorites strike at high speed and melt tiny spots. Over time, the regolith develops little particles of metallic iron, nanophase iron, formed in those melt events. That changes how the soil reflects light. It gets darker, redder in spectral terms, less like a fresh rock face. So even the dust is telling a story. Then the cutting begins. They do not hack these rocks like firewood. They slice them with diamond saws under controlled conditions, often using fluids that are carefully chosen to avoid contamination. A thin slab is taken, and suddenly you have an interior surface that has not seen sunlight in billions of years. Inside, textures appear. Crystals, bubbles, layers. Some samples show basaltic textures, dark and fine-grained, formed from lava that cooled relatively quickly. Some show coarser crystals, implying slower cooling, deeper in the crust. Some are breccias, chaotic mixes of fragments welded by impact heat, like a rock that has been shattered and glued back together. Anorthosite shows up too, lighter-colored rock, rich in plagioclase feldspar. It is part of what we think of as the ancient lunar highlands crust. The idea is that early in the moon's history, it may have had a magma ocean, a global layer of molten rock. As it cooled, denser minerals sank and lighter minerals floated, forming a crust. Anorthosite is a signature of that floating crust. It is a calm concept, a magma ocean. It sounds like a fantasy map location. In reality, it is molten stone on a planetary scale, the kind of heat that makes metal feel shy. The lab work continues with simple tests that feel almost insulting in their modesty. Thin sections are made. A slice of rock is ground down until it is thin enough for light to pass through. Then it is placed under a microscope. Polarized light reveals mineral structures, crystal orientations, tiny inclusions. The rock becomes a landscape of geometry. Chemistry follows. They use mass spectrometers, electron microprobes, X-ray diffraction. They measure elemental compositions, ratios of isotopes. The rocks do not speak, so you interrogate them by breaking off tiny pieces and asking what they contain. Isotope dating becomes one of the big quiet revelations. Using systems like uranium to lead or potassium to argon, scientists can estimate ages. Many lunar rocks come back incredibly old. Not just old as in ancient history, old as in early solar system. 4 billion years, give or take the method and the sample. That age matters because Earth cannot keep rocks that old easily. Plate tectonics recycles crust. Water erodes. Life alters chemistry. Earth is active and forgetful. The moon is inactive and obsessive. So, the moon becomes an archive of early solar system events that Earth erased. One of the most famous results is the clustering of impact melt ages around roughly 3.9 billion years ago. That helps support the idea of a late heavy bombardment, a period when impacts in the inner solar system may have spiked. It is still debated in details because science is allergic to simple stories, but the moon rocks forced the conversation. You can picture it like this. You bring back stones, and the stones tell you that the early solar system was not a calm place. It was a shooting gallery. Planets were being hit, remade, heated, fractured. The moon's face, those overlapping craters, was not just decoration. It was history. And the lab does not have dramatic moments. It has long sequences of careful work. Labels checked again, data recorded, samples subdivided and distributed to different research groups. A small fragment goes to one lab for isotopes, another for mineralogy, another for exposure age studies, measuring cosmic ray interactions that tell you how long a rock sat near the surface. Cosmic rays and solar particles leave tracks too. They create rare isotopes. They alter nuclei. In a way, space itself signs the rocks. Scientists also look for volatiles, things that evaporate easily. For a long time, the moon was thought to be extremely dry. Apollo samples supported that idea overall, but later work found small amounts of water and other volatiles trapped in some minerals and glass beads. Not oceans, not rivers, but hints that the moon is not perfectly devoid of water. It is always like this. You go looking for a simple answer and you come back with a complicated one. The rocks also settle arguments about how the moon formed. The giant impact hypothesis, the idea that a Mars-sized body hit the early Earth and the debris formed the moon, is supported by some of the isotopic similarities between Earth and Moon. Oxygen isotopes, for example, are remarkably similar, suggesting a shared origin or intense mixing. But again, details matter, and details are where scientists build their little nests of debate. You do not need to follow every argument to feel the shape of it. The moon rocks take a distant object and make it physical. They turn a bright disk into a chunk of geology with measurable properties. They make the moon less myth and more neighbor. And there is a strange intimacy in that. Not emotional exactly, more like bureaucratic intimacy. The kind you feel when you see your name on a form. You have a relationship with the moon now, and it is documented in binders. Speaking of documentation, the Apollo samples are still curated today, stored in carefully controlled conditions. Some kept untouched for future techniques that did not exist at the time. Because science is patient, and because the best way to respect a sample is sometimes to not use it yet. There are also lunar sample vaults stored in different locations because redundancy is a kind of prayer. If one collection is compromised by fire, flood, or politics, another might survive. Even rocks need backup plans, and as the labs work, slowly extracting meaning from graystone, your mind begins to wander to a simple thought. If a few people with rockets could bring back moon rocks, then nature, with far more time and far less concern for safety, has been delivering space rocks to Earth all along. You do not need a Saturn V to get an extraterrestrial sample. Sometimes the solar system just throws one at you. Meteorites are the universe's unsolicited mail. No return address, no tracking number, just a sudden arrival, occasionally through someone's roof. Most meteoroids burn up in the atmosphere, turning into brief streaks of light. The air, thick and protective, does its job. Friction and compression heating break them down. They ablate, fragment, vanish. A little bit of dust settles into the ocean. into soil, into lungs, and you never notice. But sometimes a piece is big enough, tough enough, or lucky enough to survive. It slows down and falls, not as a blazing projectile anymore, but as a dark rock dropping the last few kilometers like a tired thing surrendering to gravity. When it lands, it can leave a small crater, or it can just sit there, looking like a lump of burned stone. The outside often has a fusion crust, a thin melted layer formed during atmospheric entry. It can be black and smooth, sometimes with thumbprint-like depressions called redge-maglips, shaped by turbulent ablation. If you pick it up, it can feel heavier than you expect. Many meteorites contain iron and nickel, dense metals that Earth's surface rocks rarely have in such abundance. Your hand notices mass before your mind does. And if you bring a magnet near it, the magnet may tug. That is one of the simple field tests people use. Not perfect, but suggestive. The journey of a meteorite can be absurdly long. A rock can be blasted off an asteroid by an impact, tossed into space, and spend millions of years orbiting the sun. It can drift through resonances, gravitational nudges from planets that alter its path slowly, like a bureaucratic process run by gravity. Then one day, it intersects Earth. You are used to thinking of space as empty, but there is traffic, dust, rock, debris, a constant slow exchange. Earth sweeps through it like a runner through rain. Some meteorites are older than Earth rocks. Some contain chondrules, small spherical droplets of once molten material formed in the early solar nebula. These chondritic meteorites are like time capsules from the formation of the solar system. They have not been melted into a planet and reprocessed. They are primitive in the geological sense, meaning they have stayed relatively unchanged. Carbonaceous chondrites are especially interesting because they contain carbon compounds and sometimes amino acids, not life, but ingredients. The chemistry kit. They can also contain water bound in minerals. They are messy rocks, dark and crumbly, and they smell faintly of asphalt, sometimes when cut, because of organic compounds inside. Congratulations, you have found a rock that looks like driveway debris, but contains chemistry older than your planet. Other meteorites are differentiated. They come from bodies that melted and separated into core and mantle, like small protoplanets. Those meteorites can be metallic, likely from asteroid cores, or stony iron mixtures from core mantle boundaries. They tell you that some asteroids were once geologically active, briefly, early on, hot enough to sort themselves. You can also get meteorites from the Moon and Mars. Yes, pieces of those worlds have been knocked free by impacts and eventually landed on Earth. We know this from their chemistry and trapped gas signatures. Some meteorites contain little pockets of gas whose composition matches the Martian atmosphere measured by spacecraft. So without leaving your bed, you are living on a planet that occasionally receives mail from other worlds. The calm part is that it has always been happening for billions of years. Before humans, before dinosaurs, before plants climbed onto land, space has been sprinkling Earth with small stones, like a careless neighbor tossing gravel over the fence. Most of it burns up, but enough survives that you can build collections, classify them, study them, and learn about places you have never visited. And there is something comforting about that. In a cynical way, even if you never go anywhere, the universe still comes to you, sometimes At terminal velocity, meteorites that land in deserts or Antarctica are easier to find because they stand out against uniform backgrounds. Dark stones on white ice, unusual rocks on pale sand. Antarctica is especially useful because the ice flow can concentrate meteorites in certain areas, and the cold preserves them from weathering. Water and oxygen alter meteorites quickly on most of Earth. Iron rusts, minerals hydrate, the extraterrestrial signature gets slowly rewritten by Earth's chemistry. Earth is always trying to make everything into Earth. So when you hold a meteorite, you are holding something that is in the process of being domesticated by this planet. A space rock becoming an Earth rock, one reaction at a time. Speaking of domestication, the moon is also being slowly altered, not by rain or wind, but by space itself. Its surface is constantly being gardened by micrometeorites, churned, mixed, overturned. The regolith is a product of endless small impacts, a powder made by violence too tiny to notice individually. And that brings you back to the moon itself. Not just the rocks you grabbed, not just the rocks that fell here on their own. What makes the moon the way it is, and why does it feel so familiar from so far away? You already know the simple emotional answer. You have seen it your whole life. It rises and sets. It hangs in daylight sometimes like a mistake. It changes shape on schedule, and you learned its phases before you learned some people's names. But the physical answer is quieter and more interesting. The moon is tidally locked. That means it rotates once for each orbit around Earth, so the same face always points toward us. It is not because it is loyal, it is because gravity is persistent. Early on, the moon likely rotated faster. Earth's gravity raised tides on the moon, bulges in its shape. Rock tides, not water tides. The bulges were slightly misaligned due to internal friction, and that created a torque that slowed the moon's rotation until it matched its orbital period. Once locked, it stayed that way. A stable arrangement like a habit you cannot break, so you grow up with one lunar face. Familiar Maria patterns that humans named seas, even though they are dry basalt plains. Mare Tranquillitatis, the Sea of Tranquility. Mare Imbrium, the Sea of Rains. Names that are almost funny now, because there is no rain there, only dust. The near side has more Maria than the far side. The far side is heavily cratered with fewer dark basalt plains. This difference is still studied, but it likely relates to crust thickness and early heating. The near side crust is thinner in places, making it easier for lava to reach the surface long ago. The far side crust is thicker, resisting those eruptions. The moon's interior cooled. Its volcanic activity largely ended billions of years ago. The moon is small enough that it lost heat quickly compared to Earth. Earth keeps its internal heat longer because it is bigger, and because it has radioactive elements generating heat, and because it has convection, plate tectonics, a whole active system. The moon is mostly done. It still has moonquakes, small tremors, some caused by tidal stress from Earth, some caused by thermal expansion as the surface heats and cools, some possibly from deep interior adjustments. Apollo missions placed seismometers that recorded these events. The moon is not dead. It is just quiet, like an old building that creaks at night. Temperature swings on the surface are brutal because there is no atmosphere to moderate them. In sunlight, surfaces can get very hot. In shadow, very cold. But the regolith is a poor conductor, so temperature changes do not penetrate deeply. A few centimeters down, the temperature is much more stable. This matters for future explorers if humans ever get serious again. Digging into the regolith or building with it can provide thermal stability and radiation protection, because radiation is another constant up there. Cosmic rays, solar particles. Without a magnetic field like Earth's and without thick air, the moon is exposed. The Apollo astronauts had some protection from short mission duration and spacecraft shielding, but long-term habitation would require more. The moon is not trying to poison you. It just does not care if you are poisoned. The moon also affects Earth in ways you feel without noticing. Tides are the obvious one. The moon's gravity pulls on Earth's oceans, creating bulges. As Earth rotates under those bulges, coastlines experience rising and falling sea levels. The sun contributes too, but the moon is the main tide maker. Tidal friction slowly transfers angular momentum. Earth's rotation slows imperceptibly on human timescales, and the moon slowly moves away about the rate your fingernails grow each year. It is a slow divorce conducted by physics. The moon drifts outward. Earth's days lengthen. Far in the future, if everything else did not change first, Earth could end up tidally locked to the moon as well. One hemisphere always facing it. But other things will change first, because the universe is impatient in its own slow way. Still, the moon has been a steady partner in Earth's story. It stabilizes Earth's axial tilt to some degree, reducing chaotic swings that could make climate more extreme. It provides light at night, enough to shape animal behaviors and human culture. It has been a calendar in the sky, a clock face for early agriculture and ritual. And yet it is a wrecked stone sphere, cratered, airless, indifferent. That contrast is why it works so well as a bedtime thought. It is close enough to feel personal and hostile enough to remind you that comfort is an Earth-only feature. When humans collected moon rocks, they were not stealing pieces of a god. They were doing what humans do when confronted with something they do not understand. They took samples, they labeled them, they measured them. They tried to turn wonder into data, and the rocks cooperated in their quiet way. They gave up ages, they gave up minerals, they gave up histories of impacts and cooling. They gave up a story of a moon that was once molten, once volcanic, once battered into its current face. But rocks also withhold. They do not tell you everything. They require interpretation. They require patience. They require the humility to say, we think this is what happened, and we will adjust when new evidence arrives. Speaking of new evidence arriving, meteorites are still falling, and new lunar missions are still planned, and the moon keeps being there, turning slowly, dragging tides, holding its scars. And somewhere in a lab, even now, there are still unopened Apollo samples, sealed away for techniques that did not exist when they were collected. Because sometimes the most scientific thing you can do with a priceless object is wait. You can imagine a vault, quiet and temperature-controlled. Boxes labeled with mission numbers and sample identifiers. Pieces of the Sea of Tranquility, of the Fra Mauro Formation, of the Hadley Apennine region. Stone and dust sitting behind layers of procedure. And you can imagine the simple truth behind all of it. The moon rocks are not important because they are rare. They are important because they are specific. They are tied to a place, a context, a story, a human moment of kneeling in dust and sealing a bag. Without that context, a rock is just matter. With it, it becomes a sentence in the long, slow book of the solar system. And that book is still being written, one quiet sample at a time. The strange part is how much of that book is written in rooms that feel less like temples and more like very strict kitchens. You are standing behind glass again, watching a gray fragment become a specimen number, then a smaller specimen number, then a set of tiny chips that will be mailed across the world like awkward little postcards. You do not get to hold the moon in your bare hand. Not if the curators have any say. You work through glove ports, thick rubber sleeves that turn your wrists into clumsy hinges. You learn the slow dance of clean handling. You learn to never trust an open container. You learn that labels are more valuable than the rock because the label is what keeps the rock from becoming anonymous. The rocks sit in cabinets filled with dry nitrogen because nitrogen is boring, and boring is the whole point. Oxygen is lively. Water vapor is worse. Earth air is a crowded marketplace of molecules looking for new friends. Lunar minerals are fresh and reactive in a way that feels almost rude. They have been broken in vacuum, and they would like to stay that way. So you keep them away from the wet world as long as you can. Even the dust gets curated, not swept up and forgotten, but portioned into vials, cataloged, stored. Lunar regolith is not just gray powder. It is a record of the sun, implanted into grain surfaces, and a record of impacts, welded into tiny glassy clumps. If you heat it, gases come out: helium, neon, argon, little trapped whispers from solar wind ions. The moon has been wearing the sun like perfume for billions of years. You put a pinch of regolith into a vacuum chamber and you warm it gently. Gas molecules drift out and get measured. Not because anyone needs lunar perfume, but because those gases tell you what the solar wind was doing long ago and how long that particular dust grain sat exposed before it got buried by the next slow rain of impacts. That is how time works on the moon. Not seasons, not erosion, just exposure, burial, exposure again. You take a thin section of basalt and look under a microscope, and the crystals tell you how quickly the melt cooled. Bigger crystals? Slower cooling, likely deeper. Smaller crystals? Faster cooling, likely at or near the surface. You are reading a rock like a recipe. This one cooled in a hurry. That one had time to think. You measure titanium content in some basalts because lunar basalts can be surprisingly rich in it. You look at ilmenite, an iron titanium oxide mineral that ends up being more than just a curiosity. In the distant future, people talk about oxygen extraction because ilmenite can be processed. It is not easy, but it is possible. The moon has oxygen locked in minerals, like money locked in a vending machine that hates you. Congratulations, your treasure is mostly oxides, and you cannot breathe any of it. And still, the Apollo labs keep doing what labs do. Not dramatic leaps, quiet stacking of small facts. Some pieces get zapped with electrons in scanning electron microscopes. The surface becomes a landscape of tiny fractures and melted beads. Some samples get bombarded in mass spectrometers, their atoms sorted by weight like a very patient bouncer. Some are dissolved in acids, carefully, reluctantly, because once you dissolve a lunar sample, it is not a sample anymore. It is a solution with paperwork. The most precious samples are rationed, a milligram here, a few grains there. The lunar collection is big, but it is not infinite, and it is not replaceable in a casual way. Every new technique that arrives decades later comes with a request, a new instrument, a new sensitivity, a new promise that this time you will learn something you could not learn before. And the curators, who are the true guardians of the moon, make you justify it. You learn that science is not just discovery, it is custody. Because even after you have measurements, you still have the problem of interpretation. A rock does not come with subtitles. A rock will let you measure isotopes, but it will not tell you which event melted it. If there were multiple, a breccia is a crime scene made of other crime scenes, fragments of fragments, impact upon impact, heat, then cooling, then shattering again. It is geological recursion, a story told by someone who keeps getting interrupted. So, you build models, you compare sample ages, you compare crater counts on the surface, because crater density is another kind of clock. Older surfaces collect more craters, younger surfaces get resurfaced by lava or smeared by ejecta, and their crater clock resets. Not perfectly, but enough to map relative ages. The moon becomes a calibration target, a place where crater counting can be tied to actual dated samples. That turns into a tool for the whole solar system. You look at Mars, Mercury, icy moons, and you count craters, and you borrow the moon's timeline as a rough translation. Not perfect, never perfect, but better than guessing in the dark. Speaking of borrowing, you also borrow moon rocks for a different kind of comparison. You hold a lunar basalt next to an Earth basalt, and you notice what is missing. No hydrous minerals, no alteration by liquid water, no little chemical fingerprints of biology. Earth basalts often get weathered quickly. Iron oxidizes, minerals hydrate, the rock starts becoming soil. The moon basalt stays itself, just battered and dusted, and it makes Earth look messy. Earth is the planet of fluids. Water, air, plate motion, everything moves. The moon is the planet of stillness, with a steady drizzle of micrometeorites as the only weather worth mentioning. And once you have stared at that stillness long enough, you cannot help noticing that there are other collectors out there, other missions that go to other worlds and do the same slow work. Not with human hands, but with robotic arms and drills, because humans are expensive and robots do not need snacks. You think of Luna missions, Soviet sample returns, small automatic scoops flinging tiny capsules back toward Earth. You think of later missions like Japan's Hayabusa collecting asteroid grains, or the United States mission called OSIRIS-REx, bringing back rubble from an asteroid named Bennu. Different targets, same idea. Touch, collect, label, return. The solar system as a set of archived specimens, and every specimen comes with the same lesson. Context is everything. Because when a meteorite lands, it is context poor. You do not know exactly where it came from on its parent body. You do not know what boulder it was part of. You do not know which crater launched it. You get a rock with a long journey and a missing address label. Apollo samples in contrast, have addresses, coordinates, photos, notes. They are rocks with biographies. That is why they still matter so much, not just because they are from the moon, but because they are from a specific slope, next to a specific crater, collected in a specific sequence, at a specific time. That is what turns geology into history. Now, if you are unlucky, you get to see what happens when context breaks. A bag tears, a label smudges, a container gets jostled, a sample gets mixed. In the lab world, that is not just a mess. It is a permanent wound in the data. You can still analyze the rock, but you cannot place it properly in the story. It becomes an orphan. That is why sample curation is so obsessive. It is not bureaucracy for fun. It is the defense against meaning evaporating. And evaporating is a theme here, because the moon is very good at losing things. Not rocks, not easily, but gases, volatiles, anything light. The moon has weak gravity and no thick atmosphere. If a gas molecule gets enough speed, it leaves. If sunlight breaks molecules apart, the fragments drift. Hydrogen escapes easily. Helium, too. The moon cannot hold on to a comfortable blanket of air the way Earth can. So the moon is mostly bare. It is rock exposed to space, but not entirely. And this is where the story gets quietly weird. You might think the moon is uniformly dry, uniformly empty, but there are places where sunlight does not go. Craters near the poles with floors that sit in permanent shadow. The moon's axis tilt is small, so some crater bottoms never see the sun, ever. They are cold traps, places where water molecules can land and stay, frozen for a very long time. Not liquid water, not puddles, more like frost mixed into regolith grains, hiding like someone avoiding a conversation. How does water get there? Some of it comes from comet impacts, some from asteroid impacts, some from the solar wind itself. Hydrogen ions embedding in minerals and reacting with oxygen in the rock to form hydroxyl, then water. Little chemical partnerships encouraged by impacts and heat and time. When those molecules migrate, hopping across the surface as the day heats them and the night cools them, they can eventually end up in a cold trap and stop moving, like dust gathering in the corner of a room. So the moon is not just a dry rock. It is a dry rock with a few secret freezers. That matters because humans are always thinking about logistics. If you ever want a lunar outpost, you want water. For drinking, yes, but also for oxygen and hydrogen, for breathing and fuel. Water is chemistry that can be split, stored, used. It is a resource, which is a human word that makes everything sound like a shopping list. And it always comes back to the same unromantic truth. Space travel is not about heroism. It is about supply chains. Apollo got away with short missions, days, a brief visit, a careful touch. They did not need mines, processing plants, long-term habitats. They needed a lander, suits, and enough redundancy to outlast the worst plausible day. But future lunar work, if it becomes real, will revolve around dust, radiation, thermal cycles, and water ice that is mixed with grit. Congratulations! Your oasis is a freezer full of sand and dust, always dust. Apollo crews learned that the regolith is not just clingy, it is abrasive. The grains are sharp because they were not tumbled by water. They are broken by impacts, fractured into jagged pieces. When those pieces get into fabric joints, seals, bearings, they behave like sandpaper. Suit joints stiffen, zippers fight back, visors get scratched, filters clog. The dust is so fine that it can get into everything, and because the grains are charged, they do not simply fall off. They stick and they ride along. When you bring lunar dust into a cabin, it floats. It hangs there, sparkling in the light like something magical. But you do not want to breathe it. Those sharp grains are not friendly to lungs. Apollo astronauts reported irritation, sneezing, that odd smell. It is the moon trying to become intimate. So engineers take notes, they design better seals, they test materials, they imagine airlocks with dust mitigation, brushes, electrostatic repulsion, maybe even suit ports, where the suit stays outside and you climb into it from inside the habitat like a weird hermit crab. All of this is what happens after the romantic moment, after the flag, after the famous words. The real story is maintenance, and it makes you appreciate something else Apollo did almost by accident. They brought back not just rocks, but measurements, instruments left on the surface, retroreflectors, little arrays of mirrors that bounce laser light back to Earth. Apollo 15 put one down, and so did Apollo 11 and Apollo 14. And later missions added more. Scientists still shoot lasers at them from Earth, measuring the round-trip time. That lets you measure the moon's distance very precisely. You learn that the moon is receding, slowly. You can watch it drift away centimeter by centimeter, year by year, like a relationship slowly turning into a long-distance thing. You can also test aspects of gravity, general relativity, the equivalence principle. The moon becomes a laboratory target, a mirror on a dead world that helps you measure the living one. And then there were seismometers. Apollo left seismometers that recorded impacts and moonquakes. The moon rings in a way. Vibrations can last longer than on Earth because there is less damping, no water, no soft sediments the same way, no active tectonic grind to scatter energy quickly. A big impact can make the moon resonate like a bell that refuses to stop. It is eerie, that image, a silent world that rings when struck. Speaking of being struck, it is worth remembering what the moon is doing for you right now, even as you lie safely on Earth with air pressing gently around you. The moon is a shield, in a way, not a perfect one, but it takes hits. It draws impacts that might otherwise reach Earth. It also keeps Earth honest by reminding you what a planet looks like without weather and plates. A cratered face is what you get when nothing erases the past, and the past is not gentle. If you rewind the solar system, if you mentally peel back billions of years, you end up in an era when the inner planets were being battered constantly. The moon's crater record suggests a time when big impacts were more common. Some of those impacts would have hit Earth too. And on Earth, impacts are not just holes. They are climate events. They are sterilizers. They are reset buttons. The moon kept the record, and Earth kept the consequences. You are living on the version of Earth that survived. So when you think about Apollo collecting rocks, it is not just about where those rocks came from. It is about what Earth does not have anymore. Earth cannot easily give you rocks from that far back, unaltered. The moon can. The moon is a vault that never got cleaned out. And you can feel now why people keep wanting to go back? Not because we need more flags, but because the moon is the closest place where you can touch deep time with a glove and a scoop. But if you stay with the Apollo era for a moment longer, you notice another quiet truth. Even the rocks that came back had to be shared, not hoarded. Apollo samples were distributed worldwide in small allocations to researchers in many countries. There were lunar sample displays given as goodwill gifts too. Tiny chips embedded in resin, a little fragment of moon presented like a relic, sometimes lost, sometimes stolen, sometimes forgotten in storage. Because humans treat priceless things with the same casual care they treat office supplies. Congratulations. Your cosmic artifact is now in someone's desk drawer. And yet, despite all of that, the main collection persists. Cabinets, vaults, curators, policies. The slow discipline of not consuming your data source too quickly. It is a kind of long-term respect. You see it in the decision to keep some samples sealed. Some cores were left unopened for decades because future instruments would be better at measuring what mattered. And they were right. Later, with more sensitive techniques, those sealed cores could tell new stories. Volatiles, noble gases, subtle chemical gradients that would have been smeared by earlier methods. Science learns patience because time keeps proving it necessary. Now, if your mind drifts from the lab back to the moon itself, you start to see the surface in a different way, not as scenery, but as a map of processes. Those dark maria are not seas. They are lava plains, basalt flooded into big basins created by impacts. The impacts came first, making huge depressions. Then, the moon's interior, still warm enough at the time, leaked magma up through fractures. The lava filled the low spots and cooled, making smoother, darker areas. So the moon's face is impact scars filled with old volcanic blood. It is a calmer image than it sounds because it has been solid for billions of years. But the origin is violent. The highlands are brighter because of composition, more plagioclase-rich rocks reflecting more light. The maria are darker because of iron and titanium-rich basalt. Your eye sees it as a familiar pattern. Your brain turns it into a face, a rabbit, a man, a myth. But the truth is chemistry and history. And because the moon is tidally locked, you mostly see the near side, the one with the big maria patches. The far side, unseen until spacecraft went around, looks different, more uniformly cratered, less dark basalt, a face with fewer bandages. It makes you wonder about bias. How much of your sense of a thing is shaped by the side you happen to be allowed to see? Speaking of what you are allowed to see, on the moon, your eyes would struggle with contrast. Sunlit areas are harsh. Shadows are deep. Without air, light does not scatter. That means the dynamic range is brutal, and cameras had to be set carefully. The famous photos from Apollo sometimes look strange because of this. Shadows too dark, surfaces too bright, the sky black even at noon. Some people misunderstand that and build conspiracies out of it. But the reality is simpler and colder. There is no air. The moon is not required to look like a movie set. Your suit visor has filters, gold coatings to reduce glare. Your eyes adjust slowly. You learn to turn your head and use the edge of your visor. You learn that the sun is not just bright, it is a hazard. It can heat surfaces quickly. It can flood your vision if you look near it. You avoid it like you avoid looking directly at a welding arc. And in shadow, temperatures plummet. The regolith can be searing in sunlight and bitter in shade, a short walk apart. But the suit keeps you stable with thermal layers and a cooling garment, water flowing through tubes against your skin. The suit is a wearable climate system. Without it, you would not last long. Not because you would freeze instantly, not quite. Heat transfer in vacuum is weird. You would lose heat by radiation, not by convection. So cooling is slower than people imagine. But you would also overheat in sunlight because you cannot sweat into vacuum effectively, and you cannot convect heat away. Your body is a heat engine, and space is terrible at carrying that heat away unless you have radiators. So the suit does a balancing act. It cools you when you work. It insulates you when you drift into shade. It is an absurd compromise because physics is not obligated to be comfortable. Apollo suits did this with a liquid cooling and ventilation garment, a network of tubes and fabric. Warm water goes out, cooler water comes back. Heat gets pumped to sublimators, systems that vent water to space where it turns from solid to vapor, carrying heat away. You are literally cooled by controlled loss of water to vacuum. It is elegant and it is wasteful, and it is how you survive. Congratulations, you are air-conditioned by turning water into space fog. Now, you might expect the moon to feel utterly alien, and in some ways it does, but in other ways, it is just geology, rocks, slopes, craters, boulders. You can stand there and feel like you are on a dry mountain plateau until you remember you cannot breathe and sound does not travel and the horizon curve is too close. That closeness matters. The moon's smaller size changes everything about navigation. Distances are deceptive. A ridge looks close and ends up being a long trudge. A small crater can hide behind a gentle rise. Without familiar scale cues like trees or buildings, your brain guesses wrong. Apollo crews trained for this by doing geology fieldwork on Earth, in volcanic landscapes, deserts, crater-like terrains. They practiced with tools. They practiced describing rocks quickly and clearly over radio, because the science teams on Earth were listening and they needed descriptions in real time to make decisions about where to go next. It is easy to forget that part. The astronauts were not alone. There was a whole chorus of scientists and engineers awake and caffeinated, hearing your words and trying to turn them into a plan. You point at a rock and say, angular, fine-grained, vesicular, or glass-coated. You describe a contact between layers. You mention a boulder with white clasts embedded in darker matrix. And somewhere in Houston, someone's eyes widen because that sounds like something they hoped for. But you do not get to be poetic. You get to be precise. That is another way Apollo was different from the myth. It was not just a stunt. It was field geology performed in a hostile environment by people on a schedule. And the schedule always wins. Which is why, even on the surface, you sometimes do what is called a contingency sample. A quick grab bag of nearby material taken early, just in case you have to abort later. if the mission goes wrong, at least you bring something back. That is such a human thought. Even if everything is falling apart, grab a rock. The contingency samples ended up being valuable too, because they were still contextual. They were still from a known spot, and they still told stories. Now, when you return those stories to Earth, you do not just get ages and compositions. You get something else, quieter. You get calibration for your imagination. Before Apollo, people argued about what the moon was made of. Some thought it might be more like Earth's mantle, rich in certain elements. Some suggested different origins. Apollo data constrained those ideas. The moon is depleted in volatiles compared to Earth. It has a lower abundance of certain elements. Its surface rocks show particular histories. And the isotopic similarities to Earth push you toward a common origin. That supports the giant impact idea, but even that idea evolved. The simplest version, a Mars-sized impactor called Theia, smashes into early Earth. Debris forms moon. But then, the isotopic similarity problem appears. If the moon formed mostly from the impactor, you would expect isotopic differences. So models shift. Maybe the debris was mostly Earth mantle. Maybe there was intense mixing. Maybe there were multiple impacts. Maybe Earth was a hot, spinning mess that blended everything. Science does not give you one clean story. It gives you a family of stories, and you prune them as evidence grows. And the evidence growth is slow, because even if you have the rocks, you still have to understand the environment they lived in. The moon has no global magnetic field today, but it likely had some magnetic activity early on, recorded in magnetized rocks. Apollo samples include some that show remnant magnetization, a frozen record of ancient fields. That hints at a dynamo early in lunar history, maybe driven by a molten core and convection, or by mechanical stirring from tides and impacts. Then it faded. The moon cooled. The dynamo weakened. The shield against solar wind disappeared. The surface got more directly implanted by ions. The regolith became a better solar archive. So even the absence of a field is part of the story. Now, take that thought and pivot gently to the way the moon makes you feel familiar with it. Not scientifically, biologically. Moonlight is sunlight. You know that, but your body sometimes forgets. You see the moon glow at night, and it feels like its own light, a lantern. But it is just reflected sun, bouncing off dust and rock, and coming back to you, softened by distance and angle, not by kindness. The moon's reflectivity is actually not high. The word is albedo, the fraction of light reflected. Lunar regolith reflects only a modest amount. Asphalt can be comparably reflective. The moon looks bright because it is lit by the sun directly against a black sky, and because your eyes adjust to darkness. So when you look at a full moon and feel it is luminous, you are mostly experiencing contrast in biology. Your pupils widen. Your brain craves patterns. Your night vision kicks in. The moon becomes the brightest thing available, and your mind crowns it. That crowning shaped culture, calendars, stories, rituals. But the moon itself remains what it is. A cratered stone keeping time by orbiting. It orbits in about a month relative to the stars. But the phases repeat in about a month relative to the sun. The difference comes from Earth moving around the sun too. So the moon has to go a little farther than one orbit. to line up for the same phase again. It is a nice reminder that even simple cycles are slightly more complicated when you are inside them. And the orbit is not perfectly circular. It is elliptical, so the moon's distance varies. That changes its apparent size a little, and when a full moon happens near perigee, closer approach, people call it a supermoon, a dramatic name for a small difference, because humans love drama even when the universe offers only mild variations. The moon also wobbles a bit. Libration. Because of orbital tilt and eccentricity, you can see slightly around the edges over time, a bit more than half the lunar surface from Earth across a month. The moon is tidally locked, but it still nods and tilts like it is bored. That wobble let early observers map features near the limb more effectively, and it gave a subtle sense that the moon is not a flat disk, but a globe. Now, if you zoom out again, you realize the moon's presence is not just pretty, it is mechanical. It is gravity. It is tides. Tides are not just water rising and falling. They are energy being dissipated as heat. The ocean bulges are pulled by the moon, and Earth's rotation drags them a little ahead, because friction with the seafloor and continents resists perfect alignment. That offset bulge pulls on the moon, adding energy to its orbit and pushing it outward. Earth loses rotational energy. The day lengthens very slowly, so every night you have ever slept, Earth's rotation has been bleeding energy into the moon's orbit like a slow donation you did not approve. The evidence for shorter days in the past shows up in growth rings of ancient corals and tidal rhythmites, sediment layers that record cycles. You can infer that hundreds of millions of years ago, there were more days in a year because days were shorter. Earth spun faster, the moon was closer, tides may have been stronger. The moon is slowly migrating. In the deep future, the month will lengthen. The moon will look smaller. Eclipses will change because total solar eclipses depend on the moon being just the right apparent size to cover the sun. Eventually, the moon will be too far, and eclipses will become annular, a ring of sun still visible. Not in your lifetime, but the universe is patient, and it does not care what you will miss. And speaking of eclipses, they are another way the moon feels personal. The sky does something impossible for a few minutes. The sun gets eaten, the temperature drops, shadows sharpen, birds get confused, humans get quiet. On the moon, an eclipse is different. When Earth blocks the sun, the lunar surface goes dark, and Earth hangs in the sky as a black disk with a red ring of atmosphere. Sunlight refracted through Earth's air. The moon gets lit by all the world's sunsets at once. That is a beautiful thought, but the moon does not appreciate it. It just cools. And while you are thinking about light, you remember the retroflectors again. Those little mirrors on the moon are still being hit by lasers. The light travels from Earth to moon and back, and the timing reveals distance to the centimeter. That is how you know the moon is leaving. A little beam of light bouncing off a dead world, telling you that nothing stays put. Now, bring that back down to Earth, to the human scale. The Apollo rocks are still being studied, but not all lunar rocks came from Apollo. The Soviet Union returned small amounts robotically. Later missions returned tiny samples. China's Chang'e missions have returned regolith too. Different sites, different times, more context. Each new sample is like adding a paragraph to a familiar chapter. You thought you knew the moon, and then a new sample says, actually, here is a slightly different basalt chemistry. Here is a different age. Here is a hint of volcanic activity persisting later in some places than you expected. The moon keeps refusing to be fully summarized, and now your mind drifts to the simplest part of the whole story, the part that never required a rocket. You have always had moon rocks, in a way. Not the curated contextual kind, but fragments that arrived as meteorites. Lunar meteorites have been found in deserts and Antarctica. They were blasted off the moon by impacts, escaped lunar gravity, orbited the sun, and eventually fell to Earth. Those rocks have different values. They show you random sites on the moon, not the Apollo sites. They can broaden your sampling, but their context is lost. You do not know the exact crater they came from. You infer, based on composition and age. You triangulate possibilities. It is like getting a postcard with no city name, just a picture of a street corner. Still, they help. They tell you the moon is not uniform. They tell you different regions have different histories. They hint at the far side too. And then there are Martian meteorites, which are even more dramatic mail. You hold a piece of Mars and know it survived ejection, space travel, atmospheric entry, impact on Earth, and then human discovery. It is a chain of luck and physics. Some contain tiny trapped gases from Mars, matching the atmosphere measured by landers. That is how you know they are truly Martian. Not because they look red, because they carry a chemical signature, like breath in a bottle. The solar system is constantly exchanging crumbs, which brings you back to collecting again. The act itself, the human habit of picking things up and assigning meaning. The Apollo-era collectors were doing science, yes, but they were also doing something deeply ancient. Gathering stones, carrying them, bringing them to a home cave and showing the tribe, look what I found beyond the ridge. Only now, the ridge is space. And the stones matter because they let you test stories. Was the moon once molten? Were there big impacts? Did volcanic activity happen? How long did it last? Did the moon ever have a meaningful atmosphere? How much water is there? And where? Each rock is not an answer. It is a constraint. It limits what can be true. That is a good way to think about science in general, not as a collection of certainties, but as a gradual tightening of possibilities. The universe is huge. Your ideas are small. Data makes your ideas behave. Now, stay with that thought while you imagine the moon itself as a collector. The moon collects impacts. It collects solar wind ions. It collects the occasional spacecraft crash. It collects human footprints, and then keeps them not out of sentiment, but because nothing erases them quickly. The regolith is a blanket made of collected violence. Every grain a fragment, every fragment a tiny injury. Over time, the surface gets churned, mixed, overturned. That process is called gardening, which is a deeply optimistic name for relentless micrometeorite bombardment. A garden implies care. This is more like a neighbor constantly throwing gravel, but the result is a soil-like layer, meters thick in places, that holds history in a messy way. Glass beads from impacts, agglutinates, tiny metal iron particles, implanted hydrogen and helium, cosmic ray tracks. It is a scrapbook made with sand. If you drill into it, you get layers of exposure history, not neatly stratified like lake sediments on Earth, because impacts mix things. But still, deeper tends to mean older exposure, and you can see changes in maturity, how weathered the grains are by space. Space weathering makes grains darker because of those nanophase iron particles. That affects remote sensing too. When you look at the moon with telescopes and spectrometers, you have to account for how the surface reflectance changes with maturity. Fresh crater ejecta looks brighter. Older soils look darker and redder, so crater rays show up as bright streaks because they expose fresh material. That is why Tycho crater rays look so dramatic. It is a relatively young crater throwing bright debris across older, darker soils. The rays will fade over time as the debris gets weathered, darkened, blended. Even brightness has an age. And that helps you date surfaces relatively. Younger craters have bright rays. Older ones lose them. It is not perfect, but it is a clue. Now, in the Apollo era, you did not have the benefit of all modern lunar mapping, but you had telescopic maps, orbital photographs, and a lot of planning. Landing sites were chosen partly for safety, partly for science, flat enough to land, interesting enough to collect. Some missions targeted Maria, some targeted highlands. Apollo 15, 16, 17 went to more complex sites with mountains and rills, because by then they had confidence in better hardware. Apollo 15 visited Hadley Rill, a sinuous channel likely formed by lava flow. Apollo 16 went to the highlands at Descartes, looking for volcanic rocks, but finding mostly impact breccias, which itself taught a lesson about assumptions. Apollo 17, with geologist Harrison Schmitt, sampled at Taurus Littrow, a valley with volcanic and impact features. Each site added variety. Each site complicated the story. And if you listen carefully to the recordings, you hear it. Not just excitement, the constant describing, the constant noting, the constant awareness that they are not just tourists, they are hands for a larger mind on Earth. That is how collecting works at scale. You become a sensor. Now, let your mind drift slightly off the moon and onto something else that always sits in the background of these stories. The thing that makes every checklist feel justified. Risk. Apollo was efficient, but it was not safe in any cozy way. The margin for error was thin. A stuck valve, a bad switch, a torn seal, a guidance misalignment, a small fire. The environment outside is vacuum and radiation and thermal extremes, and the environment inside is a machine full of stored energy and oxygen. Oxygen is wonderful in lungs and terrible in cabins. Pure oxygen atmospheres make materials burn more readily. Apollo 1 taught that brutally, on the ground, when a cabin fire killed 3 astronauts during a test. That tragedy reshaped procedures and design. Materials changed, hatches changed. The entire program absorbed the lesson that even on Earth, a spacecraft can kill you. So the calm voices, the low drama, the endless checklists, they were not just style. They were survival culture built from scars. That is why Apollo collectors sound so routine. Because routine is how you keep fear from becoming noise. Now, you can carry that mood forward because it connects to another quiet truth about lunar exploration. It is not just what you bring back, it is what you leave behind. On the moon, you left descent stages, equipment, experiments, bags of waste, sometimes even golf balls, because humans cannot resist being themselves. Those artifacts will sit there for a long time. There is no rain to rust them quickly, no wind to bury them fast, though regolith slowly migrates downhill and micrometeorites churn the surface. Over very long times, dust will soften edges, impacts will pepper and eventually destroy. But for now, they remain. Future explorers could visit them like ancient ruins. A lander leg, a footpath, a piece of foil insulation shimmering faintly, a museum without air. And then there is the idea of planetary protection, which mattered more for Mars than the moon, but still hovered in the Apollo era. Quarantine was done because no one could be 100% sure. But once samples were studied, the moon was declared lifeless. At least in any active sense, the fear faded. Mars remains more complicated, which is why sample return from Mars is such a big deal. The procedures will be intense, because Mars could, in theory, have had life, and might still have microbial niches. Probably not in the dramatic movie way, but enough uncertainty to justify caution. The moon does not have that biological threat, but it has physical threats, and that is enough. Dust in lungs, radiation in cells, thermal cycling cracking materials, micrometeorites as invisible bullets, vacuum as an instant problem. Apollo handled those by being brief. In and out, minimal exposure. If you stayed longer, the hazards would stack, radiation especially. On Earth, you have atmosphere and magnetic field, shielding you from many charged particles. On the moon, you are exposed. Solar particle events can spike radiation suddenly. You would want shelter, warning systems, maybe regolith shielding. So, again, if humans ever live there, it will not be a campsite. It will be a bunker, which is a cozy thought in its own way. Humans always rebuild caves when the world gets harsh. Now, keep drifting with me, because the outline of this story still has more quiet corners to explore. You have rocks in the lab, you have meteorites as unsolicited samples, you have the moon's long memory. The next part is the emotional closeness of the moon and why it keeps pulling at human attention. Not because it is kind, because it is there. You can step outside on Earth and see it from most places. It shares your sky. It changes shape. It sets a rhythm you can notice without instruments. It is the nearest large object you can look at and recognize features on. Seas, craters, bright rays, dark plains. A face you can learn. That familiarity makes it feel approachable, and that is dangerous, because approachability is a psychological illusion. The moon is lethal to an unprotected human in minutes and hostile to equipment over time. But your brain does not feel that when it sees moonlight on a wall. It feels calm. It feels like night has a companion. That is the emotional trick. A deadly place that looks gentle from far away. And it is not just you. Animals respond to lunar cycles too. Some creatures time reproduction to tides. Some hunt by moonlight. Some hide when the moon is bright because predators can see better. Coral spawning events can sync with lunar phases. The moon is a scheduling signal embedded into biology. It is gravity translated into behavior. Humans did it too. long before science. Farming calendars, fishing patterns. The word month is tied to moon. Language itself keeps the moon as a unit of time. And yet, the moon's month is not a perfect match to human months, because humans like round numbers and tidy calendars, and the moon does not negotiate. So you build calendars anyway. You add leap days, you correct drift, you fight the sky with paperwork, very on brand. Now, while you sit with that, you might wonder about the moon's origin again, because it is hard not to. If you are going to be emotionally attached to a rock in the sky, you might as well know where it came from. The leading idea remains the giant impact. Early Earth, still forming, gets struck by a large body. The impact ejects material into orbit. That material accretes into the moon. The energy involved is ridiculous. It melts rock, vaporizes some, mixes layers. It leaves Earth hot and spinning, maybe with a magma ocean. It leaves the moon forming from debris, initially molten too. Then the moon cools. A magma ocean crystallizes. Dense minerals sink. Light minerals float, making an early crust. Impacts pummel it. Basins form. Later, lava floods some basins, making Maria. Eventually, volcanism fades. The surface continues to get peppered and churned. That is the short version. The long version is a library of papers and arguments. But the short version is enough to make you see the moon not as a static companion, but as the outcome of catastrophe. The moon is literally a scar of Earth's youth. That is another reason it feels close. It might be made partly from Earth. So when Apollo brought back rocks, in a strange way, you were bringing back ancient Earth material too, reprocessed and cooled and battered. A sibling rock, a cousin, family with a complicated past. And speaking of complicated pasts, the moon's interior is not fully dead. It has a small core, likely iron-rich. It has a mantle. It has a crust. It has mass concentrations under some Maria, where dense material makes gravity slightly stronger. Those mass cons affect lunar orbiters, tugging their trajectories subtly. Early lunar mapping missions discovered that the moon's gravity field is lumpy, not smooth. So when you orbit the moon, you are not orbiting a perfect sphere. You are orbiting a battered, uneven mass with buried scars that still pull on you. That is why lunar navigation is fussy. The moon has quirks. Even its gravity has old bruises. Apollo had to account for that. Later missions mapped the gravity field in detail, like the GRAIL mission, which used two spacecraft measuring distance changes between them as they flew. The tiny tugs revealed the gravity anomalies. It is like weighing a person by watching how the floor bends under them, except the floor is space and the person is the moon. Now, let all of this sit softly for a moment, because the theme is consistent. Everything is slow, everything is recorded, everything is quiet until it is not. And that brings you back, gently, to the human act of collecting as a way to deal with scale. When you cannot hold a planet, you hold a rock. When you cannot read the whole solar system, you read a thin section under a microscope. When you cannot travel to every crater, you date one basalt and calibrate a timeline. It is small work that points to large truths, but it never finishes. There is always another sample, another technique, another question. Why are some lunar basalts younger than expected. How much water is really in the mantle? What is the exact structure of the core? How did the far side crust get so thick? Was there one big impact or multiple? How does the moon's regolith evolve over time? And then there are the practical questions. How do you keep dust out of seals? How do you build a habitat that can survive thermal cycles? How do you store power during the long lunar night, about 2 weeks without sunlight at a given location? How do you move across regolith without kicking dust into everything? Apollo did not have to solve those. Apollo was a visit, not a residency. It was a sprint, not a settlement. But you, lying here on Earth, can feel the shape of what comes next, not in a preview way, just as a natural continuation. If you can collect and return rocks, you can imagine collecting and using resources. If you can visit, you can imagine staying. If you can map, you can imagine building. And all of those imaginations will collide with the same thing Apollo collided with: reality, procedures, dust, time. Because the moon will still be what it is, a place of vacuum and radiation and sharp powder, wearing the sun's light and keeping old scars. And the only way to exist there is to bring your own small bubble of Earth with you and maintain it constantly, like a delicate aquarium in a desert. That is where the cozy horror lives. Not in monsters, in maintenance. Now hold that idea, because it is going to matter when you think about the moon's long memory in a human sense. Not just craters and rocks, but the way the moon keeps human marks too. A footprint in regolith could last for millions of years until it is softened by micrometeorite gardening. Not erased by wind. Not washed away, just slowly blurred by tiny impacts, each one too small to notice, but together, relentless. The same goes for rover tracks, lander pads, discarded tools. Over time, they will fade, but time on the moon is deep, and fading is slow. So the Apollo landing sites are like time capsules sitting in plain sight, if you can get there. And that is an odd thought. You are used to human history being fragile. Paper burns, wood rots, cities crumble. But on the moon, in the absence of weather, history can persist in a cleaner way. Not forever? Nothing is forever, but long enough to make your buildings look temporary by comparison. Earth erases. The moon preserves, which makes it a fitting place for the last thing you might want to consider before the story drifts onward again. The contrast between how harsh space is and how ordinary the human response remains. You go to the moon and you still fill out forms. You still label bags. You still store things in containers. You still argue about data interpretation. You still lose items. You still keep backups. You still build cabinets and vaults. The universe offers cosmic scale. Humans answer with filing systems. It is almost comforting. Almost. Because if you can impose that kind of order on a handful of dust and stones from another world, you can impose a little order on anything, even on the knowledge that the universe is indifferent. But there is still more to say about that indifference and how the moon embodies it so politely, just hanging there, pulling tides, collecting impacts, waiting for the next set of hands to arrive.